What if I told you there is a storm in our solar system that's bigger than Earth, and it has raged for centuries? That's Jupiter's Great Red Spot, an enormous, mysterious vortex that has puzzled astronomers for generations. In this video, we'll dive into why it lasts so long, how it works deep inside, and what recent discoveries tell us about its future. Stick around, you might just see weather unlike anything on Earth.
Jupiter's Great Red Spot, or a GRS, is a massive anticyclonic storm in Jupiter's southern hemisphere. It's about 16,350 kilometers across, roughly 1.3 times the diameter of Earth. Winds inside the storm reach speeds of hundreds of miles per hour, or greater than 400 miles per hour in some estimates. It is located about 22 degrees south of Jupiter's equator and rotates counterclockwise because it's a high-pressure system on Jupiter. The red spot has been observed, in one form or another, for at least 150 to 300 years.
So imagine a storm you could drop Earth into, and it just keeps raging. But what keeps it alive?
Here are the main reasons the Great Red Spot can last so long. Lack of a solid surface and low friction. Jupiter is a gas giant. There's no solid ground to slow down winds via friction. On Earth's storms, ground drag and surface interactions sap energy. On Jupiter, those losses are much lower. Confinement by jet streams. The Great Red Spot is trapped between strong eastward and westward jet streams in Jupiter's atmosphere. Those jet streams act as walls, preventing the vortex from drifting away and helping maintain its structure. Deep structure and interior heat. The GRS isn't just a shallow cloud. It likely extends hundreds of kilometers deep into Jupiter's atmosphere. Jupiter radiates more heat than it receives from the sun, so interior heat could help feed convection and turbulence that replenishes the storm's energy. Feeding from smaller storms, or storm diet. Recent models suggest that smaller storms and vortices around the GRS merge into or feed energy to the red spot, helping it maintain itself. If that supply of small storms wanes, the GRS might slowly shrink. Turbulence, wave interactions, and energy transfer. The turbulent flows inside and around the GRS may generate waves, like acoustic or gravity waves, that propagate upward, depositing heat and influencing dynamics. Observations have found stratospheric hotspots above the GRS, likely from wave activity. These mechanisms combine into a self-sustaining engine. Less friction, confinement, deep roots, and continuous feeding, but it's not eternal.
Over decades, the Great Red Spot has shrunk in size. What once could engulf more than 3 Earths is now closer to 1.3 Earth diameters.
Today,
the reduction in size is accompanied by morphological changes in color, shape, intensity, and wind speeds. A recent study suggests a decline in smaller storms being available to feed the GRS may explain this shrinkage. Some scientists propose the version of the red spot we see today may not be the same storm observed centuries ago. The original may have died and been replaced. The grand mystery? Why exactly is it red? The reddening agents are not fully known. Hypotheses involve complex chemical processes, photochemistry of ammonia, hydrocarbons, irradiation in Jupiter's upper clouds. So is the Great Red Spot dying? Maybe slowly, but its deep core might persist. The visible cloud structure is what's changing first.
NASA's Juno mission has flown close passes over the GRS, giving gravity and microwave data that probe its depth and internal structure. JWST's Mid-Infrared Instrument, or MIRI, mapped temperature structure and found stratospheric hotspots above the GRS, likely from wave activity. Future work, better 3D models, more observations of small storms around Jupiter, and long-term monitoring to see whether the GRS continues to shrink, stall, or even fade. Every new observation peels back another layer of this giant storm, but we're still far from a full explanation. So there you have it. The Great Red Spot is not just a persistent storm, but a dynamic, evolving monster of turbulence, chemistry, and planetary physics. Its longevity comes from a delicate balance of constraints, deep energy sources, and a storm diet. And though it's shrinking, the beast is far from finished. If you enjoyed this dive into Jupiter's greatest storm, hit that like button, subscribe for more cosmic explorations, and ring the notification bell so you don't miss future space science deep dives. Share this video with your friends who love astronomy, and comment below, what do you think powers the red spot? I'll read out the best comments in future videos. Thanks for watching. Until next time, keep looking up.